Jai Hind everyone. I am Vivek Kumar Pansari, Assistant Professor in Department of Mechanical Engineering at Ajay Kumar Garg Engineering College, Ghaziabad. Okay, in the lecture series of shear force and bending moment, today I am actually coming to the point of shear force and bending moment. Earlier in previous two videos, I covered the basics of shear force and bending moment, in which, because we are talking about beams, so beams, different type of loads, how to find out the support reactions, how to deal with different type of reactions. So these are the essential and conceptual basic parts related to shear force and bending moment. So before going for exactly for shear force and bending moment, it is necessary to understand beams and loads properly. So today, introducing the topic shear force and bending moment, what basically it is. Okay, what is shear force and bending moment? What is the concept behind it? If I say this is a beam and it is loaded under either the point load, UDL, UVL, point moment, so what we want? This beam must resist and provide sufficient support against all types of loading. And in doing so, the beam material offers certain resistance against the force and against the bending tendency. So these resistive forces and bending moment are known as shear force and bending moment. Okay. So when the beam is loaded, the internal forces and moments are developed, and the terms shear force and bending moment comes into picture. So that's what I already told. Whenever a beam is loaded, then there develops certain internal forces and moment which resist, and which resist what? Which resist the shearing, which resist the bending of the beam. These forces and moments are known as shear force and bending moment. So here we can consider a beam which is loaded by certain point loads P1, P2, P3. Okay, these are the point loads. Reaction forces, because all the loads are vertical, so reaction forces are also vertical. For finding out shear force at any particular section, let's take a section AA. Okay, so how much will be the shear force? What basically the shear force is at this particular section AA? Okay, it will be the algebraic sum of these three, P1, P2 and R1. So shear force, we can define the shear force in terms of the definition. It is the algebraic sum of all the forces which are acting at the either side of the section plane. So where is the section plane? Section plane is AA. If I have to find out the shear force at section AA, then I have to take the algebraic sum of all the forces either on the left side or on the right side of the section plane. So here in this case of section A, there are three forces, P1, P2 and R1 on the left side of the section plane. So we are representing it, the shear force F. It can be upward, it can be downward, it depends on the magnitude of P1, P2 and R1. So F is representing what? Shear force. It is not necessary that this shear force is always on the left side. It can be on the right side also. It is on the both sides. If on the left side it is upward, then on the right side it will be downward, and its magnitude will be equal. Direction will be opposite. So again I am coming to the point. Shear force, that is the internal resistance offered by beam material against the deformation. Mathematically, it is equal to the algebraic sum of all the forces acting either side of the section plane. And on the both side of the section plane, the magnitude of shear force will be same and directions will be opposite. So this is what the shear force. Here written also. Okay, you can go through this also, whatever I discussed there, it is written here. Okay, so this force F, which I told, and it is the algebraic sum of all the forces. If I am talking about the shear force, then definitely I must talk about the direction, or the which direction will be considered as positive. So as per my sign convention, if I am taking A as a section plane, then I am considering on the left side of the section plane, if the resultant force, resultant of what? Resultant of all the external forces and reaction forces at the support. So the resultant force which is in upward direction on the left side of the section plane, it will be considered as positive. Simultaneously, on the right side of the section plane, if the resultant force is downward, this will also be considered as positive. We can take, because shearing action, I can consider the example of shearing, okay, the cutting through a scissor. So one arm is coming downward, another arm is moving upward, and both simultaneously performing the shearing action at the paper, at the cloth, and so both are considered as positive. So positive shear force, if the algebraic sum of all the forces acting on the left side of the section plane, if the resultant is coming upward, then it will be considered as positive. Simultaneously on the right side, if the resultant is coming downward, then it will also be considered as positive, because both concurrently producing the same shearing effect in the beam. Another thing which we can say here, negative kab hoga? Negative when on the left side the resultant force of all the forces acting either on the left or right side of the section plane, if it is downward, यदि सारे forces जो section plane के left side में हैं उनका sum कैसा आ रहा है? Downward, then I will say it will be negative. And on the right side of the section plane, यदि सारे forces का sum upward आ रहा है, then it will be treated as negative. Okay, so this is the sign convention. Shear force, resistive force offered by beam material against the deformation, mathematically equal to algebraic sum of all the forces acting either side of the section plane. Sign convention, on the left side of the section plane, if resultant of all the forces acting on the left side of the section plane is upward, it is positive. On the right side, if the resultant is downward, then it will be considered as positive. Otherwise, it will be negative. Now I am coming to the bending moment part. Bending moment, similar definition. Bending moment is what? Bending moment is the resistive moment offered by beam material against the deformation. Mathematically, it is equal to the algebraic sum of all the moments due to individual forces acting either side of the section plane. Now let me explain this. I have taken AA as a section. On the left side of the AA section, there are three forces, P1, P2, R1. These P1, P2, R1 are at certain distance from section AA. So there will be three moments, moment due to P1, moment due to P2, moment due to R1 about section AA. So algebraic sum of all the moments, किस किस की वजह से? Because of P1, because of P2, because of R1. तीनों moments का algebraic sum, that will be treated as bending moment. So this is what the bending moment. It is not necessary it is only on the left side. It is also on the right side, because bending कब होगा? When equal and opposite rotational tendency at the section plane. So from the left side, if it is clockwise, then from the right side it must be anti-clockwise. Then it will be producing the bending, it will be producing the curve. So on the right side also, from the definition, algebraic sum of all the moments. On the right side, how many forces are there? There are two. So because of P3 and R2, जो moment होगा section AA पर, algebraic sum of all these moments will also be known as bending moment. So again, I am concluding the definition. Bending moment, internal resistive moment offered by beam material. Okay, that is what the bending moment. Mathematically, it is equal to the algebraic sum of all the moments due to individual forces acting either side of the section plane. This is what the bending moment. Now I am coming to the sign convention. Sign convention. This is on the left side. So what it is? What is the rotational tendency here? The rotational tendency is clockwise. On the left side, it is positive. On the right side, it is anti-clockwise. So this will be treated because both simultaneously, concurrently will produce the same effect at the section AA. So both will be treated as positive. Okay. So this is the sign convention. Technically, it is also known as sagging. So it is written over here. Okay. The resultant moment about the section AA, all the loads and reaction left at the section AA is M in clockwise direction. So this is the okay. The thing you can algebraic sum of the moments about an X section of all the forces acting. I have already discussed all these points, whatever written here. It is only for the reference, so you can read also that. The direction, positive, negative sign also conveyed. Okay, this is positive on the left side clockwise, on the right side anti-clockwise. This is treated as negative on the left side anti-clockwise, on the right side of the section plane clockwise. And technically it is known as sagging and hogging. So this is the sagging and hogging. I hope it is clear. Now I am moving ahead. What is the relation between shear force and bending moment? So here I am considering a beam which is loaded through the uniformly varying load, and I am considering a very small section of length dx at which I am trying to find out the relation between shear force and bending moment. Okay, so here we can see the another diagram of this at the distance x, dx element जो यहाँ पर highlighted था. Okay, I am considering that it can be treated as UDL because the length is very small, so the variation in the load is very small. So I can consider it as a uniformly distributed load, and this uniformly distributed load को मैं एक single point load से represent कर सकता हूँ. So that will be equal to W into delta X. Okay, that is on the left side of the delta X, there will be a shear force F and M will be the bending moment. On the right side of the load dx length, there will be shear force F plus delta F and M plus delta M is the bending moment. So this is the diagram. Okay, now I will be writing the equation for this. The forces acting on the free body diagram can be shown like this. So the shear force F and F plus delta F at the distance x and x plus delta x respectively. The bending moment at x and x plus delta x are M plus M and M plus dm. Force due to external loading, if W is the mean rate of loading per unit length, I already told that the small portion of dx is taken as a UDL. So the W delta x will be a single point load which will be representing that delta x length load, and it will pass through center C. Now I am coming to the relation between them. There are two equations possible. Okay, first I am writing the moment equation about point C. So M, that is the moment on the left side of the load, F into delta x by 2 plus F plus delta F into delta x by 2 equal to M plus delta M. From where it is coming out? Let's check. F into delta x by 2, M, then F plus delta F into delta x by 2 equals to M plus delta M. Okay, so this is the first equation. By simplifying and the equation and ignoring the smaller quantities, I am getting the equation like this: F into delta x by 2 plus F plus delta F into delta x by 2 equal to delta M, which I can write in this form: F equal to delta M upon delta x. Under the limits, when delta x is tending towards 0, then I can write this is equal to F equal to dm over dx. So this is the one relation. This is the relation between what? This is the relation between the shear force and bending moment. Shear force and bending moment. This is the relation between these two. F equal to dm over dx. So this is the differential relation between the shear force and bending moment. Similarly, by taking the forces vertically and equilibrium of these, we can find out. So W equal to minus delta F equal to delta X, another relation we can establish here. So the relation, I hope it is clear. Now on the basis of these relation, we can conclude many things. We can find out many things. Okay. From the above relation, the important conclusions which can be drawn. Okay. The area of shear force diagram between any 2 points from the basic calculus is the bending moment diagram. Bending moment. What is the relation? F equals to dm over dx. So what can I write this? I can write this as a F into dx equal to dm. F into dx क्या हुआ? F into dx is the area of the shear force diagram between 2 points where the bending moment is changing by dm amount. So this is the first conclusion which we can make with the relation F equal to dm over dx. What else? So this is the m equal to F into dx. Okay, this is the area. Yes or no? M equal to F into dx, integration of F dx. The slope of bending moment diagram, is shear force. This is clear from here. F equal to dm over dx. So dm over dx is the shear force. Oh, dm over dx is the slope of what? Bending moment diagram, which is equal to shear force. This is the second conclusion. So F equal to dm over dx. If F is 0 at any particular section at particular length, if shear force is not changing, it is 0. Shear force की कोई value ही नहीं है किसी particular section में. No force is there. Then dm over dx will be equal to what? In that particular condition, dm over dx must be equal to 0. It means m is constant. So the section, the area where the shear force is 0, then in that particular case, the bending moment in that particular section will be constant. Dm over dx equal to 0. So it can be a constant, the maximum or minimum bending moment. Another conclusion which we can make, this is the dm over dx equal to 0. So what is the condition? This is the condition either for minima or for maxima. So the point where where the shear force is 0, at that point bending moment either can be maximum or minimum. So these are the conclusion which we can make from this. Point of contraflexure, another important point, or the point of inflection. Okay, here in the previous slide we were discussing about the point where the shear force is 0. At that, in that particular section, the bending moment will be constant and its value will be either maximum or minimum. Similarly, we can find another point where the bending moment is 0, m is 0. So the point where m is 0, at that point the tendency of bending is changing. That point is known as point of contraflexure. So it is the point on the bending moment diagram where bending moment changes its sign. Obviously, if it is passing through point 0, then the bending moment is changing its sign. It is from positive to negative, negative to positive, from sagging to hogging, or anything. So we can call it in any manner, but mathematically it is the point where the bending moment is 0. So this is the point of contraflexure. We can call it point of inflection also. Shear force and bending moment diagrams. When we are analyzing the beam in regard of shear force and bending moment, then for representing the magnitude of shear force and bending moment at different points, we need to draw the shear force and bending moment diagram for the ease of understanding. So shear force and bending moment diagram is basically nothing. It is the representation of shear force and bending moment at different sections. So how it will be? What it is? The diagram which shows the variation of shear force along the length of beam is called the shear force diagram. Bending moment diagram. The diagram which shows the variation of bending moment along the length of the beam is known as bending moment diagram. Now, how it is drawn? That's the point. Because on different loading, the diagram will be different. So if I am considering it, first case I am taking, that is the W. This length is L by 2. This length is L by 2. Here the reactions I am getting R1 equal to W by 2 and R2 equal to W by 2. I have to find out the shear force and bending moment equation. So how to go for that? I am taking a section at distance x. Okay. So what, according to the definition of shear force, it is the algebraic sum of all the forces acting either side. So on the left side, I am observing there are two forces. W by 2 will be treated as positive because on the left side upward it is, and it will be treated as negative. So W by 2 minus W, and the equation is coming minus W by 2. Okay. Bending moment equation I will be writing here. Okay. It is also the algebraic sum of all the moments, W by 2 into X minus W into L by 2 minus, oh sorry, X minus L by 2. So this is the, okay. How much it will be? It can I write W into X minus L by 2. This will be. Here we can observe what? We can observe two things, that the shear force, this is the equation of constant horizontal line. It is in the form of y equal to constant or x equal to constant. So it will be a horizontal line. This equation I am observing, this is the equation of form of y equal to mx plus c. Yes, we can observe here. So this will be the inclined line equation. So if a section of beam in which only point loads are there, what is there? The point load is there. Here we can write, if the point loads are there, in that particular case, the shear force diagram will be a constant line and the bending moment diagram will be a inclined line. Now I am coming to the second case, that is the UDL, uniformly distributed load. So we are taking the example of uniformly distributed load. Okay. Suppose this is the, okay, this is L by 2, this is L by 2, this is W Newton per meter is the intensity. So R1 equals to, मैं इसको पूरा ले लेता हूँ, ठीक है, and R2 equal to, how much it will be? It will be WL by 2 and it will be equal to WL by 2, R1 and R2. Now to write the equation, just take a section at distance x. Okay, I don't know where is the section is. So for writing the equation of shear force equation for UDL condition, it is the algebraic sum of all the forces acting either side of the section plane. तो इस सेक्शन के लेफ्ट साइड में देयर इज अ रिएक्शन फोर्स, पॉजिटिव होगा, लेफ्ट साइड में अपवर्ड है, एंड द यूडीएल, हाउ मच यूडीएल इज देयर? दिस मच पार्ट ऑफ यूडीएल, बिकॉज दिस इज ओनली ऑन द लेफ्ट साइड, मुझे लेफ्ट साइड कंसीडर करनी है, एंड माइनस W into X. पूरा क्यों नहीं लिया? Because it is the algebraic sum of all the forces or loads which are acting either side of the section plane. So here I am considering the left side of the section plane. This is the equation. Equation का format क्या है? Y equal to mx plus c, inclined line equation for the shear force when the load is UDL. Bending moment equation. Bending moment equation क्या होगी? WL by 2 into X. WL by 2 is the reaction, the distance from it, WL by 2 into X, and the UDL. How much UDL? W into X. डिस्टेंस कितनी होगी W into X की? W into X ये है जो सर्किल में है इधर, ठीक है ना? ये कहां पर होगा? मिड पॉइंट पर. किसके मिड पॉइंट पर? जितनी लेंथ पर स्प्रेडेड है, एंड दैट लेंथ विल बी x by 2. So wx into x by 2. Tendency of rotation कैसी होगी इसकी? On the left side, एंटी क्लॉकवाइज. पॉजिटिव किसे लेते हैं? लेफ्ट साइड में क्लॉकवाइज को. सो माइनस. द इक्वेशन किस फॉर्म की आ गई? पैराबोलिक. पैराबोलिक कैसा भी हो सकता है, ओपनिंग अपवर्ड, ओपनिंग डाउनवर्ड, बट इट विल बी अ कर्व, इट विल बी अ पैराबोलिक कर्व, स्क्वायर कर्व. सो फॉर द पॉइंट लोड, शियर फोर्स कांस्टेंट, बेंडिंग मोमेंट लाइक दिस. ठीक, यूडीएल 1 डिग्री आगे चले गए. नाउ आई एम कमिंग टू द पॉइंट UVL, uniformly varying load. Uniformly varying load. Okay, the length is L. Okay, R1, R2. Now take the section plane at distance x. Write the shear force equation. Write the shear force equation. Shear force equation will be R1 into x, R1 into x minus area of this triangle. Area of this triangle. How much it will be? मैं इसको लिख देता हूं, यहां पर अलग से ले लेता हूं. ठीक, this is x, this is what I am writing y, and पूरा ले लेता हूं, this is L, and here the intensity is W Newton per meter. So here I am writing W Newton per meter. Okay, now I can compare R1 into x, sorry, not R1 into x. I am writing the shear force equation, so why should I include x here? Okay, on the left side of the section plane, shear force R1, positive, upward. Then area of this diagram, area of this triangle, half into x into y. Y कैसे निकालूंगा मैं? How to find out y? By the similar triangle. इतने triangle को पूरे triangle से compare कर दें. So what it will be? I will be writing y upon x equal to w upon L. तो y कितना हो गया? y equal to wx by L. Y equal to wx by L. So here it will be R1 minus half into x into wx by L. How is the equation? The equation is shear force की इक्वेशन ही पैराबोलिक आ गई, एक्स स्क्वायर के टर्म में आ गई. हियर वी कैन ऑब्जर्व एक्स स्क्वायर. तो जैसे जैसे एक एक डिग्री हमारा लोड की डिग्री बढ़ती जा रही है, वैसे वैसे shear force और बेंडिंग मोमेंट डायग्राम की डिग्री भी इंक्रीज हो रही है. सो दैट्स व्हाट इट इज. ओके, एंड बेंडिंग मोमेंट इक्वेशन आई विल बी राइटिंग हियर. बेंडिंग मोमेंट R1 into x, R1 into x, the distance of R1 from this point, R1 into x minus half into, ये मैं पूरा ले रहा हूं, wx square by L. कितनी डिस्टेंस पर होगा ये? If this triangle which is on the left side, यही triangle तो है इसके left side में, okay, this much. इसको single point load से represent करना है. If I have to represent it from the single point load, this will be equal to half into x into y, and it will be at how much distance? 2x by 3. Here it is x by 3. Moment कहाँ लेना है? Moment I have to take at this point. Here is the section plane, so the distance is x by 3. Distance is x by 3. Equation कैसी हो गई? Cubic, x square into x. So this is the shear force and bending moment diagram. This we have to keep this thing in mind when writing the equation, कि how the shear force and bending moment equations will be written. So again I am concluding, point load में shear force constant line, bending moment inclined line. UDL के केस में shear force is inclined line, bending moment diagram will be square parabola. In case of uniformly varying load, UVL, shear force is square parabola, and this will be bending moment is cubic parabola. So here you will find variation of shear force and bending moment. It is tabulated here. Type of load, shear force diagram, between point loads or no load condition, it will be a horizontal line. This is the summary. In case of UDL, it will be an inclined line. In case of UBL, it will be a 2-degree parabolic curve. Bending moment, if this is horizontal line SFD, then BMD will be inclined line. UDL के केस में 2-degree parabola bending moment, 3-degree cubic parabola. So this is the summary. So here we can say कि this is the shear force and bending moment diagram. Summary इसी तरीके से हमें equation लिखनी है. Now I am coming to a very simple question, okay, related to shear force and bending moment. Very simple one. There is a simply supported beam which is subjected to uniformly distributed load of W Newton per meter of intensity. Okay, so this is the beam. Obviously, if W Newton per meter is the intensity, L is the length, then the reaction force at the ends will be WL by 2 and WL by 2. So I have to draw the shear force and bending moment diagram for this. What will I do? First, I will be getting the support reactions. So already done. WL by 2, WL by 2. निकालना आता है हमें, easily निकाल सकते हैं. Already beams पर हम question कर चुके हैं. Now for drawing the SFD and BMD, first take a section XX at distance X and write the equation for shear force and bending moment. Shear force equation, what it will be? Algebraic sum of all the forces acting either side of the section plane. इस XX के left side में या right side में? Here I am considering the left side. So on the left side I am finding there are two forces. One is the support reaction WL by 2. Another one is the UDL. So this is WX. As per the sign convention, on the left side, this will be treated as positive, and this W into X, which is the UDL, W into X, and where it will be? It will be at the midpoint of the length which is under consideration. So the shear force equation, WL by 2 minus X. WL by 2 minus WX. किस फॉर्म में है इक्वेशन? Y इक्वल टू mx प्लस c के फॉर्म में, इंक्लाइन लाइन इक्वेशन. ओके, shear force. Then this equation is valid from which point to which point? It is valid from 0 to L. This equation is valid from 0 to L. So at x equal to 0, WL by 2 minus WX, x 0 हो गया. At x equal to L by 2, at x equal to L by 2 निकाल सकते हैं हम. At x equal to L by 2, it is 0. And at x equal to L, यहाँ पर ये कितना आ जाएगा भाई? This will be equal to WL by 2 when I am putting x equal to 0. So only the thing which remains here, that is WL by 2. At x equal to L by 2, this whole terms becomes 0. At x equal to L, this becomes minus WL by 2. Clear? I am available with all the values. Now I am writing the bending moment equation. The bending moment, the algebraic sum of all the forces, all the moments. So WL by 2, this is the reaction force. कहाँ पर है reaction force? This is WL by 2. यहाँ पर moment कितना होगा? WL by 2 into x. And the moment due to W into x, it will be WX into x by 2. So that's what is written here. WL by 2 into x minus WX into x by 2. Equation is valid from x equal to 0 to x equal to L. So at x equal to 0, this term becomes 0. At x equal to L, this again becomes 0. At x equal to L by 2, at x equal to L by 2, from this equation the answer comes WL square by 8. Now we can draw the shear force and bending moment diagram. At x equal to L, this is WL by 2. At x equal to at x equal to 0, it is WL by 2. At x equal to L, it is minus WL by 2. At x equal to L by 2, it is coming 0. Inclined line की इक्वेशन थी, नेगेटिव स्लोप की थी, ज्वाइन कर दी. बेंडिंग मोमेंट डायग्राम, at x equal to 0, it is 0. At x equal to L, it is 0. parabolic equation I x square ki, and at x equal to L by 2, the value is coming WL square by 8. So parabolic curve which is opening downward because minus x square hai. Okay. So like this we can draw the shear force and bending moment diagram. We can find out the shear force and bending moment equations also. This is the very simple problem which I discussed here today. But if you are interested in other problems which are slightly complicated, then you can refer my previous videos related to same topic, shear force and bending moment, already available on YouTube channel of AKGEC. So thank you very much for watching the video. Thank you.